Hey, what's up everybody? In this section of this course, we're going to go over the two pointers pattern. The two pointers pattern is basically exactly what it sounds like. We're going to make use of two pointers to keep track of two data points simultaneously, which is going to level up our ability to write more efficient algorithms. We'll start with a simple example that will present you all with a clear picture of what I mean when I say that we can keep track of two data points simultaneously. To better illustrate this technique, I've chosen a problem that's not in our Leetcode patterns list for this first example, but don't worry. The problem examples following this first one will be part of the Leetcode patterns list. So the problem that we want to take into consideration for this first problem is this one here. We're asked to find two numbers in an ascending ordered array of numbers that add up to a target value. The array is guaranteed to have exactly one solution. That is, we can rest assured that there are exactly two numbers within the array that add up to the target value. And by exactly, I mean exactly, no more, no less. And for some strange reason, the array is one index, so we'll need to keep that in mind as we work through this problem as well. So let's imagine that we have an array that looks like this, and a target that is 22. And we want to find the two numbers in this array that add up to the value 22, the target. The naive solution to solving this problem would be to iterate through this input array, and for every index of the array, check every other index's value to see if the two values combined equal our target. As you can see, this solution isn't very efficient because we are unnecessarily iterating through elements that we've already seen before. That is, when we're calculating all of the values in the array with this first value 2, we already see every other number in the array. So in theory, after that first round, we've already accessed the two values that result in 22, those values being 7 and 15. But even so, we still won't realize that with this solution until our second trip around when we calculate all of the values in the array with the second value, 7. Now let's try to visualize the more efficient solution using the two pointers pattern. So remember that two pointers means exactly that. We're going to use two pointers to keep track of two separate values simultaneously. So let's imagine that we have the same array and the same target, 22. This time we'll place a pointer at both ends of the array, hence two pointers. Following that, we simply add the value at the first pointer and the value at the second pointer together to see if they add up to our target. If they don't, we simply check to see which pointer we should move inward by taking into account whether or not our calculated value is less than or greater than our target value. So the important point here is that our array is an ascending ordered array. That means that the values at the end of the array are going to be larger than the values at the beginning. So if our calculated value is greater than our target, that means that we need to decrease the size of our calculated value. We do that by moving our rightmost pointer to the left because remember, the further right we go, the larger the numbers become. So we want to use a smaller number for our addition because our result was larger than the target. Same for if the result wasn't large enough. We'd move our smaller number pointer on the left to the right to increase the value of our addition. And as you can see, this is a much more efficient way to solve this problem. Now let's get into writing some code. For this pattern, and most likely for the rest of the patterns in this course, we're going to be using Python. But don't worry, if you're familiar with any other programming language at all, you won't have a problem following along with this course. So let's first briefly go over how to install Python. The installation process for Python starts at Python's website here, which I will also link in the description. So to start, you'll just want to go to this Downloads tab and then download Python 3 for your operating system. After the download is complete, you'll be able to access the installer, which is self-explanatory. Once you've completed the Python 3 installation process, you should be able to check that the installation was successful by typing in python 3 -- version at the command line. Most likely my Python version will be different from yours. I have an older version, but as long as you have the most updated version, you'll be okay for this series. Okay, so once you've installed Python 3, you should be good to go to start writing some code. So we're going to go ahead and make a directory using the P flag to create nested directories. And if you don't know what I mean by that, you can go ahead and type in man make dir and just search for the P flag. And it tells you right here that this P flag just creates intermediate directories as required. And without this P flag, if you try to make a directory that has nested directories, it's going to throw an error. So we're going to go ahead and do make dir p python source coding interview patterns. And then we'll go ahead and change directory into that directory. And within that directory, we want to make another directory called 2 pointers, because that is the pattern that we're going to be working with. And for me, 2 pointers directory already exists because I already created it here, but for you, it will not exist yet. Then we'll change directory into the 2 pointers directory. And within this directory, you want to create a directory called 2sum2 and change directory into that directory. And the first thing that we want to do before writing the algorithm for this problem is we want to set up a virtual environment, which is basically a means to isolate the dependencies for our application. In this case, we're not really writing an application or building an application. We're just going to have one Python module that contains the code for our problem solution. But nonetheless, we're still going to create our virtual environment and make sure we're running it. So we'll do Python 3 -mvenv, and we'll just call the virtual environment folder venv. And now within this directory, we'll have a venv folder which contains our virtual environment. And if you ls this venv folder and the bin folder within it, you'll see that we have all of the binaries that will be used while we're working within this virtual environment. So for example, right now, if I do which Python 3, it's going to give the path to my global Python binary installation. But once we run our virtual environment by doing source venv/bin/activate, and I do which Python 3, I'm now using the Python binary that's within my virtual environment folder. And that's how the virtual environment is going to work for all of the binaries that we install while we're running within this virtual environment. So our environment is essentially what's contained within this venv folder. So let's go ahead and clear that, and we want to create a file, and we're going to call it naive.py. And actually I said that we're only going to create one module within this directory, but I was wrong. We're going to actually code the naive solution for this problem, as well as the more efficient solution to this problem as well, using 2-pointer technique. So we'll go into this naive.py file, and we'll define a method called 2sum2, and we'll do nums and target, and we'll just do for I in range length of nums. So we're going to iterate through our nums array, and for every iteration of our nums array, we're also going to iterate through that same array starting from whatever index that we're on. So for j in range, and this range is going to start at our current index plus 1, and it's going to end at the last element of our nums array. And we're just going to see if nums I plus nums j equals target, we're just going to return I plus 1, j plus 1. And that's because they want us to return the indices of the two numbers that add up to our target. And the reason we're adding plus 1 is because the nums array is actually a 1-indexed array as opposed to a 0-indexed array. So the first index of the nums array is actually 1 as opposed to what's usually 0. And we can see that here, given a 1-indexed array of integers numbers, they want us to return the indices of the two numbers. And I don't think it matters what order we return the indices in. Or maybe it does, but yeah, we'll just return the first index and the second index. So as we can see here with this nested for loop, in the worst case, we're going to have to iterate O of n square times. And although this seems like a very minimalist solution because the code is short, it's actually not performant at all. And I think in some cases, we actually won't even be able to complete the problem with this solution because we will exceed the amount of time allowed to process the actual algorithm. So let's go ahead and test this out. We need to create an entry point to this function. So we'll do if name equals main will print toSum2, and we're going to pass in the values from the example for the problem. So we'll just do this first example. So we'll pass in this array, and as the target we'll pass in 9. So nums is going to be this, and then our target will be 9. And we can go ahead and save this. And as we can see here, the expected output is 1 and 2, because the values at index 1 and 2, so this is index 1, this is index 2, the values here add up to our target 9. 7 plus 2 is 9. So if we do python 3 naive.py, we should get 1 and 2, which we do. So we've seen the naive solution, so now let's go ahead and see if we can do better with our two-pointer solution. So we'll go ahead and clear this, and we can create a new file called tosum2.py. So now we have two files and our virtual environment, and we'll just cat everything from naive.py into our tosum2.py file. And then we'll open our tosum.2.py file, and we can just go ahead and delete this. And now we're free to code up our more performant solution. So we're going to create variables for our two pointers. So we'll have pointer 1 equals 0. And you can name these pointers whatever you want. I'm naming them pointer 1 and pointer 2 just to make the pattern more clear. I want to emphasize the pattern more, is what I'm trying to say. And let's go ahead and format this. So one pointer is going to be at the beginning of our nums list, and the other pointer is going to be at the end of our nums list. We're going to bring both pointers towards the middle of our nums list until our left pointer, or pointer 1, is no longer less than pointer 2. So to do that, we want to do while pointer 1 is less than pointer 2. Then we'll get the result for the sum of the values at those two pointers. So nums pointer 1 plus nums pointer 2. So this is going to be the calculated sum for this iteration. And we're going to do some simple checks. We're going to check if the sum is equal to our target. And if that's the case, of course, we can just return pointer 1 plus 1, because remember that it's a one-indexed array, and pointer 2 plus 1, because remember they want both values or indexes to be returned in a list. So if the sum is the target, then of course we just return. But if that's not the case, we want to check to see if the sum is less than the target. Now this is where things begin to get a little bit tricky. So for this problem, the nums array is an ordered array. That is, the values closest to the 0th index of the array are going to be lesser values than those close to the end of the array, because it's an ordered array from least to largest. And as you can see in the problem here, it says that is already sorted in non-decreasing order. So it's sorted in ascending order. So that means the last element of the array is going to be the largest value, and the first element is going to be the smallest value. So that means if our sum is less than the target, that means that the value at pointer 1 is too small. So we need to move that pointer up one index, because we know the value at the next index is going to be larger than the value at the current index, because it's an ascending array. And if this is getting confusing, don't worry, as usual, I will do a visualization. But for now, pointer 1, in this case, will need to be incremented, because if we're at the value, the first index of the array, and we add one of these values to the second pointer to this value, and it doesn't add up to our target, that means we need a larger value here. So we're going to increment 1, because we know the value at the next index is going to be larger than the value at the previous. And that's a mistake. So if the sum is less than the target, we'll increment 1. But if the sum is greater than the target, we've gone too large. So we want to decrement pointer 2. And that's because, for example, the same reason, but just on the right end. For example, if the value here added to one of these other values exceeds what our sum is, of course we want to decrease the value. And we can't decrease the value by moving to the right from the pointer 1 because that'll just increase the value. So we need to decrease our right pointer or pointer 2. We need to decrease it to decrease this total sum. And that's going to be it for this algorithm actually. And that's the most confusing part of the algorithm. But other than that, this should be good to go. So let's go ahead and save this. And once again, we're going to expect the values 1 and 2. So we'll go ahead and do Python 3. And we'll do this time, we'll do toSum2.py. And we get 1 and 2 as expected. So let's go ahead and get into the visualizations for both the naive and the more efficient solution. Okay, first let's go ahead and take our naive solution into consideration. So for our example input for our target, we'll use the value 9. So let's say target equals 9. And our nums array will look like this. 2, 7, 11, and 15. And for this solution, we simply iterate through every element of nums for every element of nums. For I in range length nums, so we'll start with our I being equal to the value here, and we can just go ahead and add the indexes in there. So we have our indexes here, and we're going to start at this top for loop here. So we're going to start at the 0th index for this top for loop. And then we're going to go into this nested for loop where we're basically going to iterate through this index, I, the top for loop's index plus 1. So this index plus 1. So in the second for loop, we're going to iterate from this index, our I's index plus 1, all the way up until the end of the array. So we're essentially going to be comparing this value here to every other value in the array to check to see if any two values within the array equal our target 9, or which for that matter, because we're guaranteed to have two values in this array that equal the target. So j is going to start off as I plus 1, so we'll do j is the green, so we'll just write here j for green and I for red. And we're going to end up at this line here where it says if the value at nums I plus the value at nums j equals target, then we're going to return those values. But if they don't, of course, we're not going to do anything. We're just going to move back up to the top of this for loop and continue to iterate. So here we're going to check if 2, the value at 0 is 2 and the value at 1 is 7. We're going to check if 7 plus 2 equals our target 9, and it actually does. So we would end up returning this here. And the reason we're returning plus 1 is because the problem says that the array is 1 indexed and not 0 indexed. So we need to add a 1 to account for the fact that the actual array is 1 indexed and not 0 indexed. So for example, index 0, if we add a 1 to it, will become index 1. And in a 1 indexed array, the index would look like this: 1, 2, 3, 4, starting from 1. So that's why we're adding the 1 here to each of these indexes. And this was a relatively short solution, so I couldn't really show you the entirety of the algorithm. So let's just pretend for a second that our target isn't 9. Let's pretend that our target is 22. So in that case, these two values would not add up to our target, so we wouldn't do this. We would just go here, which means that we would increment our j. So this would move up. And then once again, we'd end up here and we'd compare 11 plus 2. 11 plus 2 does not equal 22, so we wouldn't do this here. We'd move back up to the top here. So this would move up again. And then we would add 15 plus 2, which is 17. 17 does not equal our target, so we wouldn't do this. And we're at the end of our for loop here, so we'd go back up here. And this one would iterate. And it would move here. Then we'd end up here again, where it would be j in range I plus 1 up until the length of nums. So our I is index 1. So I plus 1 is index 2. So this would move here. And we'd compare 7 and 11. 7 and 11 is 18. So we wouldn't do this. And this would move up 1. And then we'd add 15 plus 7, which is 22, which is our target. So then here we would return the index for I and the index for j plus 1. So as you were able to see here, for every iteration of our nums array, we essentially had to use this nested for loop to iterate through that same array once again. And the time complexity, of course, for that is O of n squared. And that's because for every iteration of nums, in the worst case, we need to iterate n times. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So in the worst case, for each iteration of nums, we need to iterate again n times. And here we have a square. Because here we have n and here we have n. So we have n columns and n rows. And to get this area, we just do n times n, which is the same as n squared. And that's why this naive solution is O of n squared. So now let's go ahead and get into our more efficient solution here. So for this solution, we're going to be using the 2 pointers pattern. So we'll have the same input for nums 2, 7, 11, 15, and the same target, which is 9. And in this scenario, we're going to have a pointer and we're going to have it point to the first index of this array, and we're going to have a second pointer which is going to point to the last index of this array. So the length of nums minus 1 is the last index of the array. And then we're going to use a while loop, which will just continue while pointer 1 is less than pointer 2. And that just means that while the index for pointer 1, as it traverses up, while it's less than the index for pointer 2, then we'll continue the while loop. Because once pointer 1's index is no longer less than the index for pointer 2, that means that the pointers have met. So let's draw this out. Pointer 1 is currently here. And pointer 2 is currently here. And actually, let's just put the indexes in here as well. So 0, 1, 2, 3. And pointer 1 is currently at 0, and pointer 2 is currently at 3. So this while loop, while pointer 1 is less than pointer 2. Because if pointer 1 becomes 2 and pointer 2 becomes 2, they're equal. We want to finish this while loop. And what we're just going to do is we're going to start by calculating the sum of the values at these 2 pointers. So the value at 0 is 2 and the value at 3 is 15. And 15 plus 2 is 17. So the sum here would be 17. And we want to just first check if the sum is equal to the target. So 17 is not equal to our target 9. So we're not going to return yet. And this is the important part here. So if the sum is less than our target, we're going to increment pointer 1, so we're going to move pointer 1 up. Or if the sum is not less than our target, then we're going to decrement pointer 2. We're going to move pointer 2 in this direction. And the reason for that is because if the sum is less than our target and this array is in ascending order, it's an ordered array that's in ascending order, we know that the next value is going to be greater than the current value. And if the sum is less than our target, it isn't yet high enough to equal our target, then of course we need to increase the sum somehow. And the only way to increase it is to make the lower number larger by moving it up our ascending order array. Because if we were to move this down, then we'd decrease the size of our sum. But the sum is already less than target. We want it to be equal to target. So we need to move this pointer up, which increases the size of our sum. So currently pointer 1 is at 2 and pointer 2 is at 15. And 15 plus 2 is 17, but our target is 9. So our sum is not less than our target. Our sum is greater than our target. So we need to actually decrement pointer 2 to decrease the size of our sum so that we become closer to 9. Because if we decrement pointer 2, we know that the value that's behind our current index is less than the one at our current index, because an ascending order array is going to have the largest value at the end, right? So we're going to decrement pointer 2. So pointer 2 will now point here because we subtracted 1 from 3, the index 3, and now it's 2. And then we'll end up back here at the top of this while loop, we'll end up here. And then we'll add these two values to get our sum again. So now we have 11 and 2. 11 plus 2 is 13, which is greater than our sum. So sum is not equal to target, so we don't do this. Sum is not less than target, it's greater than target, so we're not going to do this either. We need to decrement our pointer 2 once again, because we need to decrease the size of our current sum. 13 is too big, and we know that the number behind this number is going to be less because this is an ascending order array once again. So we're going to decrement pointer 2 once again. So we'll move this to point to index 1. So we subtracted 1 from index 2, which left us with index 1. Now pointer 2 is pointing here, and we end up back at this for loop again. Pointer 1 is still not less than pointer 2. Pointer 1 is 0, pointer 2 is 1, and we'll calculate the sum once again. So now we have the value 7 plus the value 2, and 7 plus 2 equals 9. So our sum here is 9. Then we check if sum equals target. Our sum is 9, our target is 9, so this would resolve to true. So we would return both of these values with 1 added to them because it's a 1-indexed array. So we found the 2 values in this array that equal our target. And as you can see, that's a whole lot more intuitive than iterating through the entirety of the array for every value in the array. So let's go over our time complexity. So as you saw here, this while loop is going to terminate once pointer 1 and pointer 2 meet. So that means that in the worst case, we're going to iterate through the entirety of this nums array, but no more. And the reason I say that we're only iterating the one time is because pointer 1 and pointer 2 are never going to overlap, or pointer 1 is never going to go past pointer 2 and continue to iterate down the array. Once they meet, the while loop is going to finish. So pointer 1 is going to iterate through 1/2, more or less, and pointer 2 is going to iterate through another half, more or less. Of course, it's not always going to be half. Like in this situation, pointer 2 went most of the array and pointer 1 just stayed in the same position. But I think you understand what I mean. Both pointers aren't going to iterate through the entirety of the array individually. Both pointers will share the work, and one pointer will never do the work that the other pointer already did. So we're only going to touch each element in this array one time. So that's why our time complexity is O of n. The time scales linearly with our input nums. And our space is, of course, O of 1. Because we're not using any extra space or anything, our space is constant. And that is going to be it for this problem. I hope that you all were able to learn something, and I'll see you in the next one.